Hey everybody, today I want to talk to you a little bit about valence bond theory and orbital hybridization. I'm going to start today by giving kind of an introduction and overview to this concept, and then we'll conclude with an example which will hopefully help illustrate what I'm talking about. So Lewis theory states that bonding happens, specifically a covalent bond happens when we share valence electrons. And valence bond theory agrees with that. The element that it adds is the atomic orbitals. So we haven't considered where those electrons are until we get to valence bond theory. And essentially what it says is that if you've got a half-full atomic orbital, okay, in atom 1 and a half-full atomic orbital in atom 2, those two half-full orbitals can overlap and they form the covalent bond from a molecular orbital. There are really then two types of overlap that can occur. The first of those is called a sigma bond. That's when you get a direct overlap. And you see three examples on your screen of the different ways atomic orbitals can directly overlap. The top one, A, being two s orbitals overlapping directly. The middle one, B, is an s and a p orbital overlapping directly. And the bottom example, two p orbitals overlapping directly end to end. Those are all different ways that you can get a direct orbital overlap. And this is known as a sigma bond. It is the first bond that is formed between any two atoms. The second type of bond is a sideways overlap. This is known as a pi bond, and as shown on your screen, those bonds only occur by sideways overlap of p orbitals. And when you form a pi bond, what you are actually forming is a double or a triple bond between two atoms. And those double and triple bonds are less flexible. They restrict rotation between atoms. So if we consider atomic orbitals, and we'll look at a very simple example to consider this, and that is CH4. And if you look at CH4, we all know that it's a tetrahedral molecule that is one carbon bonded to four hydrogens. Well, if you look at the electron configuration, specifically the valence electron configuration, the orbital box diagram of which is shown on the left of your screen, you note that carbon only has two half-full valence electron orbitals, and hydrogen only has one. This means that from valence bond theory standpoint, carbon could only bond to two hydrogens. And you see that represented in the center of your screen with the blue and red diagram. Not only that, but if you consider standard atomic orbitals, the bonds between carbon and those two hydrogens would only occur at 90-degree angles. So A, standard atomic orbitals don't explain the number of hydrogens that bond to a carbon in methane, which is 4, and B, they don't explain the bond angle that we observe with methane, which is 109.5 degrees, or a tetrahedral molecule. How do we account for this? Well, what we do is use something called hybrid orbitals. And this is a combination of orbitals from the atomic orbitals. So we take the regular atomic orbitals, the S and P that we're used to, we sort of throw them into a blender, and we produce some equivalent, degenerate, or equal energy orbitals. Typically, those degenerate orbitals are slightly lower in energy overall than the atomic orbitals we start with. We won't worry about the specifics of how that mixing happens or why. We just want to be able to look at a molecule and understand what kind of result do we get if we have this molecule. So that's kind of where we're headed. We should, though, understand the rules that are behind hybridization. So first of all, only central atoms in structures tend to hybridize, okay, and they only hybridize the orbitals that they need. So it's always a little bit random in that sense. In other words, it may not be all the atomic orbitals on that center atom that are hybridized. And I'll show you an example and talk about that in a minute. Okay. Ultimately, what you get is 5 possible hybridization schemes, and we won't look at all of these in detail in this video because that would be kind of overwhelming, I think. But they are SP, SP2, SP3, SP3D, and SP3D2. And I'll tell you which each of these hybridization types, which type of molecules they correspond to in just a minute. Okay? The one thing that you should know is that the number of atomic orbitals that you put in does equal the number of hybrid orbitals you get out. So let's return to our methane example, CH4. Okay? Carbon, we know, has an s orbital, the 2s orbital, and then the 3 2p orbitals that are holding its valence electrons. And you see those pictured in red and blue here. You throw those guys into a blender, as we'll call it, and what you get out, and these are shown in purple, are 4 sp3 hybridized orbitals. Those are 4 equivalent orbitals where you can take the 4 valence electrons, following all of the rules we know about electron configurations, and put one of those electrons in each orbital. Carbon then gains the ability to now bond with 4 hydrogens, or 4 other atoms for that matter, which it didn't have before we did this hybridization. Coincidentally, and we'll move to the next slide here and I'll show you a picture of this, we also get the appropriate bond angle because we get the lowest energy or the minimized energy conformation of the orbitals. So in this picture, what is shown in purple are the 4 sp3 hybridized orbitals on the carbon. What is shown in blue, those are the 4 s orbitals, one on each hydrogen, and you notice they overlap end to end, forming a direct overlap or a sigma bond. So if we use hybrid orbitals, we get the appropriate geometry or bond angle, and we get the appropriate number of bonds available to the central atom. That's really why we do this. Okay, well that's great, but looking at a molecule now, how do I know which hybridization scheme it might undertake, and what do each of those schemes look like? This slide kind of gives you a summary in the table on the right, and it turns out that the hybridization scheme is directly related to the electronic geometry that we used to determine in Vesper theory. Okay, so you count the number of electron groups, say you end up with 2 on the central atom, then that molecule has a linear electronic geometry based on what we know. Turns out that that is an sp hybridization, sp. Okay, and that's shown in the top of this table, and you can work your way down the table and look at the different electron groups and the different hybridizations that occur. The one we looked at is kind of in the middle here with the 4 electron groups, tetrahedral sp3. The methane example we just looked at uses that hybridization. It is also worth pointing out that if you have 2 or 3 electron groups, then you're going to have an extra p orbital, at least 1, if not 2. Okay, that's where you get double and triple bonds. So if you have 2 electron groups and it's linear, you have 2 extra p orbitals because you only use 1 of the 3 possible p orbitals, which means you can form up to 2 more pi bonds, giving you a triple bond possibility. In the 3 electron groups with trigonal planar electronic geometry, now you have 1 extra p orbital, and so you can form double bonds. The tetrahedral one in that sense is sort of less interesting, the sp3 hybridization, but if you go to sp3d or sp3d2, the 5 and 6 electron group hybridizations, these account for the expanded octets that we had seen previously. This is perhaps best illustrated to you working with a real molecule in a real example. So let's do one problem before we end the video today. And so the question posed here is determine the electronic geometry, molecular geometry, and hybridization for each interior atom in C2H4. Also determine the total number of sigma and pi bonds in each molecule. Okay? Well, we better draw the Lewis dot structure for C2H4 to begin with. So let's do that. The carbons in this case are in the middle. Each carbon has 2 hydrogens attached to it. And turns out that to make carbon have its 4 bonds and its octet, there is a double bond between the carbons. We'll label the left carbon, carbon 1, and the right carbon, carbon 2, for purposes of our discussion. And if you look at each carbon, regardless of which one you look at, you notice both carbons have 3 electron groups around them, which means they have a trigonal planar electronic geometry. And since all of those electron groups are bonding, they also have a trigonal planar molecular geometry. And if you remember back to the chart I just showed you, a trigonal planar electronic geometry corresponds to sp2 hybridization. So carbon 1 and carbon 2, same electronic geometry, same molecular geometry, and an sp2 hybridization. If you look at the structure, you'll notice we drew 6 total lines. 5 of those lines are sigma bonds. The lone pi bond is right there. The double bond between the 2 carbons. So the second bond formed between the 2 carbons. And on the right of the screen, you see a little bit fancier representation of all of the orbitals that are here. Again, the purple orbitals are the sp2 hybridized atomic orbitals. Okay, there's 3 of those on each carbon. The red orbitals are the pi bond orbitals. Those are formed from the leftover p orbital on each carbon. And then the blue orbitals are the s orbitals on hydrogen. I hope this helped explain a little bit better what hybridization is and what valence bond theory is. And I look forward to seeing you all again when we talk about our next fun chemistry concept.